An old time in the way that he was with the Edmonton Center for years and years and years, and he's part of this program where the Edmonton Center is leading our center. We've got a lot of well-documented information about it. So Bill Toon, but Bill has been hiding in the weeds. He's been here for 13 years. And he's been a member of the Edmonton Center, and he just swung over as he saw the light finally. We're most happy you joined us, and I hope you'll come out and see us at various events. So, let's see here. Okay, so tonight's program, we'll have some announcements, upcoming events, and our guest speaker tonight is Dr. Alan McConnachie. I call it the Monarchia Spectroscopic Explorer, but really, his official title of his talk is called Canada's Role in the Next Generation of Wide-Scale Spectroscopy. So we'll talk a bit more of that. After the meeting, we usually go up to the fourth floor lounge on the Elliott Building for cookies and coffee and conversation. And Diane will have the library open and things like that. So please remember to do that. Announcements. As a president, I'm going to go into a due diligence mode right now, and because in about January 19th, RASC signed a new authorization with Transport Canada. And I just want to make sure people are aware of it. It's regarding handheld lasers, and the short story is that handheld lasers will be only used outside a 10-kilometer radius from all the certified aerodromes as described in the interactive map. Now, they did have some weasel words underneath it, and when I was at Astro Cafe on Monday, I demonstrated the practicality or impossibility of filling out the form. It's just crazy. So effectively, if you're on the Sandwich Peninsula or in Victoria, you are not allowed to operate one of those green laser pointers at a RASC event. So just keep that in mind. And if you're away from those circles, basically what we're supposed to do is have one person as the operator and one person as a watcher. And both of them have to take a course, and the course is a PowerPoint presentation, and it's not available yet. So we have a bit of an issue there. At any rate, well, so that's my thing. So green laser pointers in Victoria, won't be using them in the building. So the Vice President is not here tonight. Sky News Editor and Star Party Captain Bruce.
Captain Star Party. Right now the preparations are going quite well. We only have one thing we need someone to step up and do, and that's rent 12 to 15 chairs for our Starbecue and general outdoor use. Just those kind of plastic chairs. The ones you see out at bus stops, preferably we don't take those chairs. Kind of bad about that sort of thing. And for the Sky News, as per tradition, this month is going to be between end of this month and next month meeting. That's when it's going to be issued as per tradition. So that's what's going on with that.
Well, thanks for stepping up and doing that, Bruce. So that the Star Party is going to take place starting on Friday afternoon and evening of the 27th of September at St. Stephen's Anglican Church out in a beautiful valley in Saanich, and hopefully we'll have some clear skies. We tried it last year, and Kevin called it a cloud party, not a star party, so I thought that was rather cheeky. But, and I think Diane actually saw something at about 2 in the morning. That was about the only
schedule. It's 10 minutes each in the comment.
Yeah, so.
I paid for it.
At any rate, so let's see. Our treasury report, Deb?
Okay, we have two outstanding checks, and once those are cashed, we will have $10,479.53.
Very good.
Yeah.
Membership, yes.
I'm Chris Purse, past president and membership coordinator. We have 273 members currently. We'll be attending an event at the location of the Astro Cafe on Saturday afternoon next week, which I remembered we forgot to mention this past week at Astro Cafe. So we're looking for people for 2 hours to help out at the Fall Fairfield Fete, I think they call it. And there'll be information table and solar telescopes if conditions permit.
Very good.
And the other thing is I'm going to be coordinating the calendar orders this year, so I have a sign-up sheet. There'll be $15 again. So if you'd like a 2020 RASC Observers calendar, please see me at some point. We'll be getting an order in pretty quickly, but we'll order kind of sufficient numbers that we should have enough.
Are you collecting funds tonight as well?
I can start doing that if you want to pay, yes.
Okay. Well, thanks for both the Paul Fairfield and the calendar thing. Thanks for stepping up.
And magazines on the front, if anybody doesn't have one.
So, Sky News. So if anybody doesn't have a copy, help yourself here. Next is schools program. Sid.
I don't have very much to say as we are just starting our program, and except I have good news. We got new volunteers, 4 new volunteers to replace 1 temporary absence. Lori will be for 2 months incapacitated, but so we got good news. We got more involvement for our membership, so that's good. Yeah.
That's excellent. Okay,
Yeah.
thanks, Sid. Matt is not here. Normally Matt is setting up a camera to televise this on the web, but he couldn't be here tonight, I guess. Joe, website anything?
No report on the website. It seems to be running fine, but I just will say the Rascal Star Party t-shirts I have with me. So if anyone would like one, see me after the meeting or up at the Astronomy Lounge, and I can sell you one for $15 for adult size and $13 for children's size. And if you pre-ordered, please let me know so I can cross you off.
Okay, thank you. Michelle's not here for observing, and Nelson is not available about the National Council. But we do have our national president, Chris Diener, here. Chris, would you like to say any words of maybe about the announcement?
Just a couple things. Our General Assembly for 2020 is taking place in Vancouver, June 5th, 6th, and 7th. It's nice and close, and you know, none of us, at least with the exception of me possibly, are on the hook to help organize the thing. So it's a good opportunity. Now this General Assembly is going to be a little different from the ones in the past, because we are going to be holding a lot of the events in a hotel. I think it's the Executive Inn or something like that, and it's in Coquitlam near Lougheed Mall. I know at least one evening's events are going to be taking place up the hill at SFU, because Vancouver Centre has actually kind of become a bit more aligned with SFU than UBC is in the past. And we're trying the hotel for a couple of reasons. At SFU, their residences are not going to be available because there's some huge construction project going on. And also, there's been a lot of talk about maybe we should try a GA in a hotel as opposed to a university, because as the folks who helped organize GAs here, I'm looking at you, Laurie, will know there's often a lot of huge hassles involved organizing universities. The rooms are less expensive, but it introduces lots of problems. So we're gonna try the hotel. So the rooms are going to be more expensive than what you might be accustomed to, but I think a lot of people going to Vancouver, they can they tend to stay with friends or relatives or things like that when they're there. I think that was kind of the experience last time. And this hotel, because it's close to the Lougheed Mall, is close to the SkyTrain line, so it's fairly accessible if you're not staying on site. And you had a question?
Yeah, what are the dates?
I've heard a number. It's north of $100 a night. So.
How much?
And I think it's sort of about 150 in that neighborhood, but anyway, we'll have to. Actually, I'm going over to the Vancouver Centre tomorrow night to sort of, talk to them and see how things are going and encourage them a little bit. Because they kind of took this, at a later stage than what we would normally be doing that. So anyway, I hope to have more information as we go along. So anyway, and I hope you noted the date. This year we didn't meet on a long weekend. We've decided we've had it with long weekends. And this one, the one in Toronto this year was in the Father's Day weekend, and this one is in an even earlier weekend, the 5th, 6th, and 7th, which unfortunately is my wife's birthday weekend, but anyway, you just can't avoid it, I guess. Yes, and I'm looking forward to it because that's what I'm retiring as president. But so that's one item. And the other news, which we just announced today, is that our executive director, Randy Atwood, is retiring next month, and he's been our executive director now for 5 years, and he's just had kind of an amazing life in the RASC. He was president of the Toronto Centre. He's younger than me, and he was president of the Toronto Centre, God knows when, in the 80s or something like that. And then he became national president. He became national president 20 years ago at our GA at Pearson College. And then, but he wasn't through. He founded the Mississauga Centre. He lives in Mississauga, so they have a really good center going there. I'm going to be speaking there next month. And then he came back to be our second executive director. He's done it for 5 years, and because he is quite a good astronomer himself. He's been a great spokesperson for our society. And so anyway, he's decided he thinks that 5 years is enough, so we're looking for a new one. And we just announced that today. So if you're interested in being executive director and live in the Toronto area, the job is open. There's a listing on Charity Village, the Charity Village website. So that's the big news right now from the national scene. So, any questions or anything? Okay.
Okay, thanks very much, guys. That's great news that we have a GA so close to it. I hope a lot of people will try and get over for it. I'm going to be kicking my grandson out of his crib, so I can deduct the $100 fee or whatever it is. So I'm looking forward to that. Upcoming events. Just a reminder that our Victoria Center observatory sessions now are on a Saturday rather than a Friday. They're on a Friday on a weekend during the summer to avoid conflicts with the Saturday star parties at the DAO. And the Astro Cafe opened its doors last Monday, and it'll be open pretty much every Monday in the Fairfield Community Center. And thanks to our hosts, Barbara and Kurt Lane, as well as Chris First and John McDonald. Are you decided if you're going to open on long weekends, or are you debating that?
I don't think we can. So we were saying that.
We decided not to because of the chair issue.
Yeah.
So they're not in the calendar.
I see, okay. But that might be subject to review. We can talk to the people. Quite often they'll deliver the chairs, but I don't think it's okay. On Saturday the 21st is a really busy day. It's the first day of a Fix and Site workshop at the center of the universe. And Joe Carr is organizing that. Joe, there's still some space available?
There is, if anyone would like to sign up at the last minute. I think the early bird rate is still available.
So Fix and Site is kind of the Swiss Army knife of astrophotography processing, and it's the powerhouse that a lot of people are learning to use. And the people who are giving the course, Warren Kellner, is kind of an authority on it. He's written a very useful book that a lot of people need to get through that complicated program. And Paul Fairfield was mentioned. But the Friends of the DAO, of course, they have an AGM that night as well. And we have a VCO session that night. So there's four events. I just hope we haven't signed up for any science literacy events, have we? Good. Well, last year we signed up for 2, I think. It was really, it seems to be a day that's kind of dangerous. So I mentioned the Star Party. The next monthly meeting will be in B150, just down the hall in the Fleury Hall. And Linda and Thomas Philipper from JPL will be giving a talk there. And so we look forward to that. But mention was made of Toronto and the GA that we have down there. And the next speaker, Dr. McConnachie, gave a talk at the GA, and he's going to do an encore presentation here tonight. So Canada's role in the next generation of wide-field spectroscopy. Alan studied it at St. Andrews in Scotland, and then he got his PhD at Cambridge, and then he moved out to the west. I mean, he's been milling around the Victoria area, both at the UVic as an adjunct professor at times, I think, and up at the DAO, and he's now senior scientific officer at the DAO, and his real passion is galaxies and dwarf galaxies and things like that. He's also involved in this very exciting role for how we can deal with our telescope. And I was just talking to them this morning, and I was this evening, and I said, well, basically, when I first saw the telescope in the DAO, I was 10 years old, and the telescope was 41 or 42 years old at the time. And I realized the brand new telescope we have, the Canadian-French Hawaiian telescope, is 40 years old now. So, whoa, I was physically shaken. At any rate, so this telescope is going through a midlife crisis. And we've got a brand new makeover plan for it, and Ellen's going to share the information about this exciting new project. Thank you for coming.
Thank you. And I apologize to anybody who was at the General Assembly, because this talk is really very similar to the one I gave there. But hopefully you can still get some interest. I'm going to try and click this one. 14 years ago, 11 of which have been spent in the DAO. Jim hired me, which is very nice of him. And my interests are, as you've just heard, generally all to do with nearby galaxies, dwarf galaxies, resolved stellar populations, so the galaxies that you can see the individual stars of when you use big telescopes, which is a very small number of galaxies, right? But you can look at those in exquisite detail. When I moved to DAO, I was originally there as a postdoc before I went into a continuing position. I started, because I was there, getting a little bit more interested and a bit more sort of involved in instrumentation, because of course DAO is absolutely fantastic, and DRAO, its sister, are absolutely fantastic at developing instrumentation for Canadian facilities, for international facilities. And that's quite interesting. I find that quite stimulating. And so there were a couple of projects going on at the time, a high resolution optical spectrograph for Gemini, which is now actually nearly built. And this thing, which emerged during my time as a postdoc. This is called Into the Future with CFHT, because one of the other joys that I have in my job is that I get to think not just about the stuff that I do specifically, but also about all of the other things that Canada is doing in astronomy. And that's actually a heck of a lot. In terms of the international facilities, in terms of the science that those facilities enable, it's really quite astounding. I have not had a course in how to use this, so everybody be safe. But this is a bunch of some of the facilities that are starting to exist. When I started out, all of these things were literally just, renderings and computer renderings, and now some of these things are not. This is not, for example. What we have here is you have three extremely large telescopes. The European extremely large telescope, the Giant Magellan telescope, and the 30-meter telescope. And this is the one, of course, that Canada is very deeply involved. We have a couple of space telescopes here, Euclid. This is going to be launched in about 3 years' time, something like that, which will be doing a lot of work relating to the nature of dark energy and how the universe is expanding with time. And WFIRST is sort of like an American version of that, but slightly different. Then you have things like the large synoptic, the large LSST. This is a major facility I'll come back to later on, back in the sky. This is the square kilometer array. This is the NGVLA, Next Generation Very Large Array, both radio telescopes. And this is one of the coolest things around, and it doesn't get enough press in my opinion, which is Gaia. And Gaia really is transforming everything we know. Anyway, that's just a snapshot of some of the facilities. Canada has a massive role in actually quite a few of them, but particularly this facility here, the 30-meter telescope, is something which, it's a massive international endeavor. You'll have seen it actually in the news, not for actually very good reasons recently, and I'll touch on that later. But what this actually enables is phenomenal. And it's actually, when you actually then find out what Canada is doing in that, that's quite phenomenal too. So I'm going to start this talk a little bit by actually just sort of giving you a little flavor of the context of where we are with facilities and telescopes in astronomy, and why you need another telescope, and what's this one doing versus what other things are doing. But if you look at something like the 30-meter telescope, you can ask, well, what is that doing? Okay, so here is a beautiful image. I believe this is the VLGs in the southern hemisphere looking towards the center of the galaxy. And they're firing a laser up at the center of the galaxy because they don't like it. But what that enables them to do actually is to take very, very high resolution images of the very center of the galaxy. And this is using a technology called adaptive Vortex. And what that then allows you to do is phenomenal type stuff. And this actually, the simulation here came from Keck. It's not a simulation, these observations came from Keck. And what you see here, if this starts playing, there we go, is actual stars moving around on time scales of months, or weeks, months, years. These are the stars that are orbiting, or appear to be moving. You can see they're tracing out very nice elliptical orbits. And that implies that there's something awfully big and awfully massive right in that center bit there. And that's called Sagittarius A star. And that is the strongest evidence that exists that we know of in science for a supermassive black hole, which is exactly what it says. It's an absolutely massive thing, which is predicted, I guess, through Einstein's general relativity and such like. But it is basically a point mass, which is about 1,000,000 times heavier than the sun, right at the center of the galaxy. And you can actually measure those observations. Now, if you look at this, this is 0.05 arc seconds. Okay, an arc second, of course, being 1/3600 of a degree. So this is remarkable spatial resolution. And that kind of science is going to be kind of lame, actually. What we can do now is going to be really lame in the future. Because what you can then actually do with TMT dwarfs all of that. If you take something like that image, and then you actually say, well, what would it look like if you were to look at it with TMT? That is what you then end up seeing in a 20-second exposure. But 20 seconds gets you that picture. Well, the number of stars there, the amount of information in that field is utterly incredible. The spatial resolution there is absolutely incredible. It's never been approached before. And with that sort of technology behind it, the sorts of tests that you can do of, say, Einstein's theory of general relativity by looking at the center of the galaxy, looking at those orbits, is phenomenal. And this is, of course, the 30-meter telescope. This has been it's been a priority now for decades for Canadian astronomers to be part of an extremely large telescope. And many people have been working very hard on this. In fact, that entire, when you start from the outside, that entire dome is built by, or will be built by a Canadian company. You keep changing the names. I think it's Dynamics. It used to be Dynamic Structures Limited, but it might now be Empire Dynamics Limited, which are a BC company. And so they're actually going to be building that. But what's even more phenomenal than that is the science that I showed you before, the picture that I showed you before of the center of that image is because of the adaptive optics system. Okay, now adaptive optics is the thing that takes the twinkle out of starlight. Okay, you know, stars don't actually twinkle, of course, you all know this. But by firing lasers up into the sky, you can basically have reference points that then allows you to correct for the distortion induced by the Earth's atmosphere, because you can see what the point should look like, and so then you can correct the light that comes in by basically deforming the mirror. And doing that is incredibly complicated. And Luke Samar, to these days, he's been my boss sort of almost since I got there. He's always been the sort of, well, he's always been the person I report to. These days, he's actually the new Greg Kalman. He's the new director of HA. He was the TMT instrument scientist for many, many years, and he had this beautiful phrase which he basically calls nefarious the heart of TMT. And you know, in terms of technology, it's the thing everybody wants. The entirety of nefarious, the complete system, all of it is being built by Canada. All of it is being managed by people here in Victoria. And that's kind of incredible, actually, when you think about that. That this exceptionally complex astronomical device is entirely Canadian. This is a project which involves India, it involves the United States, it involves Japan, it involves China. No doubt it will involve the US and others as well in the future. And yet all of it is being done by Canadians, in fact, centrally really here in Victoria. And you might ask the question, well, how on earth did that happen? You know, like, yeah, that's kind of incredible. And when you ask the question, why that happened, a part of the story, at least, comes back to looking at, well, what has Canada been doing? And the Canada has been doing astronomy on Mauna Kea, which is where the OTMT will be, for many years. First light for Canada Trans-Hawaii Telescope was 1979. It is older than I am, when measured by such measures. And as you move around, you also see another facility which Canada is heavily involved in. Over on the other side here, you're about to see Gemini South. A 4-meter class telescope in 1979, an 8-meter class telescope in the 90s. The precise date escapes me right at this moment. But both of these two facilities, Gemini North and Gemini and CFHT, both of them Canadian, CFHT of course very, very heavily Canadian, both of which have provided essentially a platform for the development of Canadian astronomy for a very long time, but not just in terms of the science, but also in terms of the technology. When we look at CFH, it had a history of first, it was the first major telescope, big telescope, at a phenomenal site. And because of that, it was really the first in its class, or it was the best in the world for a very long time. It wasn't until HST and the Keck telescopes were built that it basically became sort of a second tier, but even then that second tier was still incredibly powerful, and it became the best in class. And even now, over the past decade or so, it's sort of adopted a new mode of operations. But during all that time, it's had an amazing number of instruments. Some of the first instruments of their type were ever built there. And it really has phenomenally good atmospheric qualities. It's located in arguably, not just Mauna Kea being one of the best sites for astronomy on the planet, if not the best, but people who are in the know about Mauna Kea will also argue that the CFHT location on the mountain is also the best location on the mountain for looking at the sky. In 1994, Pueo was built. And Pueo in 1994 was the first major adaptive optics system on a telescope, full stop, or major facility, full stop. And the image that you could get from seeing the blurry image there to this much sharper image, which you see lots of nice area rings with diffraction rings around them. This diffraction limited image was taken in 1993, and that was led and contributed to by many people, of course, but particularly people such as David Crampton and others at DAO at Victoria. And because they had that experience, when the 8-meter telescopes were starting to look for what they wanted to do something like this, Gemini North and Gemini South, both of them are infrared optimized, and adaptive optics is easier to do with these longer wavelengths. So they wanted to do an AO system for telescopes as well, for the 8-meter telescopes as well. And so then, because of the heritage in 1994 of Pueo, they were then well placed. This is Glenn Harrison, Anthony Andre Anthony. In 2003, Gemini Altair was built, and Gemini Altair was the facility class adaptive optics system, such that basically you could kind of just push a few buttons and all of a sudden you could get a fraction limited usage of Gemini, and it's still in use today actually. It's being upgraded, of course. But again, because in 2003 you then had a group that had built an 8-meter class adaptive optics system, then, well, going from this to this thing that you can now stand over, to what TMT Nefarious will be, this is a person here, and this entire system is the thing that goes on the side of the telescope that instruments then plug into, right? This is not the telescope, this is not the instrument. This is the thing that you need to have in order to have the instruments work, right? And it's absolutely A, enormous, and B, massively complex. And I mean massively complex. Glenn Harriott, who was you saw in the previous picture here, there's maybe 2 to 3 people who understand the entirety of Nefarious. And Glenn is the systems engineer for the entire thing, so is largely responsible for this, along with people like Dave Henderson and Columbia and others. And that's what's being built now. And why are we able to do that? Well, because we had that heritage, right? Because you actually had a facility which at the time was the best in the world, you did something amazing with it, the next facility that came along wanted a piece of that action, and they turned to the people who were the experts, and that was Gemini Altair. And now, something else is coming along, and really the adaptive optics group at DAO is now second to none in the world. And not only have we been looking at very narrow field instruments, CFHT, of course, when you're doing adaptive optics, you're looking at a small patch of the sky and incredible resolution. They've also been doing very wide field astronomy. more sort of astronomy that I said is my kind of bread and butter stuff. And they had, for what was for many years the largest mosaic camera in the world. You had 40 very large CCDs covering a 1 square degree focal plane, so arranged like this, the moon roughly, or thereabouts. It's a massive micro camera, and again taken from a fantastic, taking images from a fantastic site allows you to do some fantastic science. So let's talk about my science for a second. But this is a picture of M31, M33 scaled according to Keynote. So as we can, these two, of course, as you know, are about 15 degrees apart on the sky. And 400 such pointings of that megacam camera allows you to create an image of this, where this is not actually an image of the light. This is actually an image of the density of stars. So essentially, we're looking at the number of stars in all of our megacam frames, and particularly the stars that, because of their properties, we think belong to M31 or to M33 to the triangle. And then you can actually make a map, which is essentially the equivalent of a surface brightness map. It's the equivalent of seeing very, very low surface brightness. The only difference is that these sort of structures here that you're seeing are more like they'd be about maybe 32 or 33 magnitudes per square arc second, which, as many people know, is at least about 100 times fainter than can possibly be done on any of your major astronomical telescopes in terms of looking at the integrated light. But you can instead map the entirety of the empty space surrounding these galaxies, and you realize they're not at all empty. Most of these blue dots here are nice dwarf galaxies, many of which weren't really discovered as part of the survey. All of these streams, structures, triangle here, you can see has sort of this stuff being cooled off of it, or this flux surrounding it. And again, these are stars which we think is the sign of an interaction between Andromeda and Triangle in the past, and you can do lots of stuff like that. Alternatively, one of the surveys that's most well known, the CFHT and Megacam, is the CFHT Legacy Survey. And here, they survey hundreds, if not thousands, square degrees, but you can do lots of different science with all of the objects that you find in that, be it science in the galaxy if you're looking at the stars close in, or stars or galaxies very, very far away. Here, what they're actually looking at is supernova, and measuring the properties of supernova, and from that actually able to measure the values of omega m, the density of matter here, the omega lambda, the density of dark energy, essentially. And the bottom line of these contours is this was and remains one of the actually best measurements yet of the cosmological properties of the universe in terms of how much dark energy is there, what's the rate of expansion, and things like this. So that's been a massive contribution. Bottom line, CFHT over many years has pioneered narrow field stuff, has pioneered and it really is focused on largely in the more recent years wide field science, be it cosmology, be it galaxies, stellar populations. Right now, however, deep surveys of the sky are getting kind of old. And by that, what I mean is the next thing that's going to come along is going to completely wipe out everything that's been done before. This is the LSST, a massive, the Large Synoptic Survey Telescope, where if you look here, this is basically just a simulation of pointing on the sky. Its field of view is very large, many, many square degrees. But if you just look, so say all of this is happening during a single night, and you can see the area of sky that it's surveying per night. It's going bam, 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 bam. Changing goes about every 30 seconds or something like that, reading out an absolutely enormous camera in seconds, which actually is not, I mean, the technology there alone is phenomenal. And so this is mapping the sky regularly. I think it maps the entire sky every few nights and essentially all of the bands, and it keeps on doing this repeatedly and repeatedly and repeatedly. And from that, the amount of science we can do in terms of the time domain, seeing how things change, is remarkable. When you add up all of those images and get a very, very deep stacked image of what the sky looks like, the amount of the faint objects that you can see, be they faint stars in our own galaxy, be the galaxies very, very far away, low mass galaxies with extremely high redshift and such like. The science that you can do is absolutely incredible. And it's actually been described to me before that basically LSST is essentially a massive software project with the telescope front end. right? Because in terms of the amount of data that you have, and how much you need to process and how quickly you need to process it, the bit at the front that gets you the data is your sort of least problematic thing that you're going to be dealing with. But this is going to be happening soon. In fact, this was the image as of May. This is not computer rendered. This is actually, I'm pretty sure I should have downloaded the most recent one, but LSST is starting to very much exist and will be starting to do science in about 2021, 2022 timeframe. Okay, so that's very, very soon. Both begs the question, really. I mean, CFHT is now frankly old. It's about 40 years old. And so what next for CFHT? And I like to phrase the question in this respect, should it have a future? And why? Which is to say, I don't actually subscribe at all to arguments of this has been really good in the past, you should do something with it in the future. I don't actually agree with that at all. These things are really expensive. Unless you have a really good reason to be doing it, don't do it. Is my own argument. Everybody's a little bit different. Clearly, I have a lot of love for CFHT, and I believe it has, could have a fantastic future, but only if you have a fantastic idea. Otherwise, close it down and do something else. That's my own personal view. So, should it have a future? What could it be doing? So now let's talk about what you'll see is become MSc. This is, again, a sort of snapshot similar to the one I showed you at the start of a whole load of things that are happening in astronomy right now. These are the extremely large telescopes. This is LSST and Subaru, which has Hyper Supreme Cam, both amazing lighting cameras. These are all the various space missions. Gaia, which is phenomenal. I'll comment on that later on. Euclid, WFIRST, these are all surveying the sky. Mostly here for looking at galaxies, here mostly looking at the Milky Way. You have things like Rosita, which is an X-ray survey telescope. Plato, which is looking at planets, or looking at very, very, very bright stars, so planets. The SKA, I should have presented you VLA as well in this. You have things like ALMA, you have Spica in space, you have also potentially a white dwarf complement to ALMA that people are talking about. You have a vast number of things there. And when you look at that, you sort of go, that's an incredible sort of network of facilities. Because the reality of how people do astronomy these days is not, this is my telescope, I'm going to do my thing. It's, okay, I can access all of these telescopes, and because I know all of these people, I can collaborate with all of these people. And so essentially, this is my playground. What is that I want to be doing? When you look at that and think, well, actually, what don't we have? Well, you realize you actually have things like, the very precise measurements of very faint sources well covered. You have mapping. Almost all of these things over here are mapping, figuring out where objects are. Things like this will, identify billions of objects, and we'll get colors for those objects by looking at them in different filters. Same for all of these space-based missions as well. Similar kind of story at longer wavelengths, though of course the technology is a bit different. When you actually look at that, many people and many committees around the world, many different countries have looked at this, and they ask, well, what is missing? What they keep coming up to, but what we came up with, was there is no way to get the sort of complementary spectroscopy that you would like. Once you find you have billions of sources here, and you know that they're blue, that's kind of unfair actually, LSST will tell you more than just that. But once you sort of know their broad colors, well, wouldn't you like to know something else? Wouldn't you like to know about their chemical composition? How are they moving? What's their velocities? And things like this. In order to get that higher order information requires spectroscopy. But if you have billions of sources, then frankly you're never going to be able to follow up on all. But you'd like to at least follow up some significant millions of them. But how do you do that? Well, you need a very, very large telescope to complement the fact that this is actually sort of a 6-meter telescope. So you want to have a large telescope to be able to then get spectrals. You need to be covering the white field, and you need to get an awful lot of spectra at the same time in order to do this efficiently. And that is essentially what MSc, the Monica Spectroscopic Explorer, is designed to do. And that is the original idea behind what we now call the Monica Spectroscopic Explorer. We came up with the idea in 2010, it became MSc properly in 2014. It's now 2019, 2027, we hope that it will get built before the end of the next decade. To give you just sort of give you a quick primer here, this is the Hubble 3D field. Again, you can see amazing sources, and then taking the images is the. I mean, obviously, this is where the passion for astronomy comes from, right? Seeing these pictures. But in order to do a lot of the sort of astrophysics, well, you can do an awful lot with the picture. You can do an awful lot with the pictures in different colors. But spectroscopy is really where you then get the idea, right? Very simply cast a light through a prism, and you get a spectrum. And then by measuring the intensity of light as a function of wavelength along here, you might see emission lines. This is some galaxy which has some H alpha. The emission which shows you something, as it turns out, about star formation properties of the galaxy. How fast is it forming stars? It tells you something about O2, and you see other lines here, O3, O2, H beta. Together, these things tell you about how fast the galaxy is forming stars. It tells you about how much chemical enrichment of the galaxy there has been. By measuring the positions of where you see these lines versus where you actually know the line should be, you can see the spectrum has been shifted. That allows you to measure a velocity or a redshift for the galaxy. That then allows you to tell you something about how it's moving through space. And so there's a vast amount of information you can get, and that's for a galaxy. Similar kind of story for a star. And so MSE, well, multi-object spectroscopy, and the whole MSE idea is that we need to replace. We need a 10-meter class telescope. I need 10 meters because we're going to be looking at very, very faint targets, things like LSST or big telescopes. They're identifying faint targets that we want to follow up. We need to look at a very wide field all at one time. So this is the sort of size field of view that we're talking about. Several millions across 1.5 square degrees or thereabouts. And then you install a suite of spectrometers to measure the spectra of multiple astrophysical sources. And by multiple, I mean a lot. In terms of per pointing, MSE will record about 4,200 objects will have their spectra taken simultaneously in that 1.5 square degree field of view. And so again, the information content that you have because of that's really quite remarkable. Many of you might know Dennis Cranford, who was the director at DAO, of course, for a while, and is still there. Dennis is very good value, of course. And he came up with this. He says he came up with this, but this is so clever that I do wonder. But if a picture is worth 1,000 words, a spectrum is worth 1,000 pictures. And I like that very much, actually. In terms of what you can get, that's probably about right. In terms of what you can learn about the sources of the study. There's some major pillars here with respect to MSE, of course. Though, I mean, yes, the technology is sort of obvious when you look at the suite of capabilities that we have, but there's some key science that you then design the facility around. One of these is the formation and evolution of the distant galaxy. And I say the distant galaxy because we have technology that allows us to look at stars which are very nearby. But stars in the outer parts of our galaxy are much harder to access. This, you'll notice, is a picture of the Milky Way, except it's moving, right? Because this is what Gaia is able to do. Gaia is recording all of the star-like sources, all the point sources in the sky that you see. And it's about 1.6 billion sources or something like this that it's detected. And it is measuring their positions and their magnitudes. And that sounds really lame. Like, as I know, it's measuring positions. So, it will measure precisions for the brightest stars to 1 micro arc second. And it is measuring precisions to 1 micro arc second. Okay, a micro arc second. You want to Okay, so a degree, means about half a degree across. Okay, that's great. And so an arc second is 1/3600th of that. A degree. Okay, so that's 1/1800th of a full moon. Okay, that's small. And a micro is a millionth of all of that. All right, and so that's a bit small. Okay. So I might talk for an hour. If I bore you during that hour, please, I will stop earlier. But to put that in context, a microarc per second is the distance my hair will go, that you will see my hair go in a period of 1 hour when viewed from a distance of 100 meters. Right? And if that doesn't blow you away, then think about that, and at some point it will blow you away. And that's what we are able to do. And that, I think, is phenomenal. You know, like people design this, right? It's not like this technology. You know, technology doesn't happen, people create it. So we can measure how far my hair goes in a period of 1 hour when viewed from a distance of 100 meters. And that's phenomenal. That means that you can actually then measure so many things, how planets are moving as stars, as the planets move around the star and the star wobbles because of that gravity. You will see that for a huge number of stars. One of the biggest sources of contamination, one of the biggest sources of distortion that Gaia has to deal with is the gravitational distortion caused by the solar system as the planets are moving around the sun. That distorts, because of Einstein's relativity, that distorts space-time so much that that's actually one of the biggest sources of distortion that has to be removed in order to then see my hair. Okay? I mean, this is amazing stuff. So because of this, we are starting to understand how things move in the galaxy very well. And how things move generally because of gravity. That means we start understanding the mass very well. We understand where all that mass is. We know already, and Gaia is confirming, that much of that mass is actually dark matter, it's stuff that we cannot see. And we can also actually then see that not just that there's a disk, but that there's all these other different structures and substructures within the Milky Way. That then tells us about things about how that galaxy is actually being put together. Why are these stars moving the way they are? Well, something must have caused them to move that way, so what were they doing in the past? Okay, and in that scenario, this is, you know, the simulation of the collapse of a whole bunch of dark matter to form a halo inside of which our galaxy forms. There's a whole theories which we developed before Gaia, actually that, as to how our galaxy can be put together. And that very dynamical process, here you're just looking at what the dark matter would be doing, that very dynamical process leaves imprints, right? It's now the case, and because of Gaia, we know how objects are moving this way on the sky much better now than we know how objects are moving this way. It used to be you could measure radial velocity very easily, right? And you still can. And it used to be that knowing how things move this way is really hard because the motions are so small. Gaia is now measuring those motions, and it's doing it for about 1.6 billion objects. We don't have radial velocities for 1.6 billion objects, so we don't actually know this part of how those stars are moving. If we knew that information, we would have almost complete information. And that's what MSD will do in very large numbers. It will also, of course, for all of those stars, be able to look at their chemical composition. So at the same time as you're looking at the dynamical formation of the Milky Way and seeing that sort of also blueprint in the dynamics of the stars, you're able to see the chemical signatures as well. You know, what were the supernova that went off? What elements were made of the supernova that contributed its material to form this star some millions or so years later that we are now observing with MSD and with Gaia. So understanding how our galaxy forms, that's obviously a pillar of many, many science cases. And the sort of facility MSD exists already for like 2-meter class telescopes and 4-meter class telescopes. It does not exist for on 10-meter class telescopes, and in doing so, you can actually mean that you can now study the entirety of the galaxy, not just the very nearby regions of it. These are maps of, you know, what the galaxy might look like just in spatial information, but if you measure the metallicity content and the chemical content of all of the stars, these are the structures you might see. And MSC will be able to do all of that. Another sort of major pillar, the only other one which I'll speak of before we move on to other things, is galaxy formation cosmic noon. And what does that mean? Well, SDSS, Sloan Digital Sky Survey, it's kind of like a 2-meter MSC, right? It was basically a multi-object spectroscopic survey, taking spectra of a huge number of objects, but on a 2-meter class telescope from a fairly rubbish site. And nobody's going to be offended when I say that. But it's done an absolutely amazing job because it was just dedicated. It only did one thing, and it did really, really well. It took spectra of galaxies and stars. And this is the volume of space that XCSS showed by measuring the redshifts, you're measuring essentially the distances. And this is a very beautiful fly-through that's been made of the XCSS data set. where all those galaxies are. In fact, the images of some of the galaxies that were then retrospectively examined. There are a large number of galaxies in this data set here, several million that take part here, and that's fantastic. It took about the legacy survey, I can't remember exactly. SSS is still going strong. It's about 14. It's done about 14 different data releases, so it must be about 15. No, it must be like 20 years old now. But the main part, which is based took about the first 5 years or thereabouts to do. That's phenomenal. MAC will do that in 7 weeks. Whereas, this is imagine this was the entirety of the universe and this is us at the center. FCSS, the very nearby, all of that is sort of very nearby galaxies. The LSC universe goes all the way out to sort of essentially as far as you can see because we have such a sensitive telescope. We do something equivalent to the data richness of SCSS about every 7 weeks, and we hope to be going for a couple of decades. And what that then allows us to do is that galaxies nowadays, I have a colleague who works more in this area than I, and galaxies now seem to have done all of the really exciting things. They've been assembled, to the large part they've been assembled now. And we think sort of soon after the Big Bang there was this big epoch of galaxy formation when basically the star formation rate, the number of stars that were forming the function at the time was really high. Okay, that's what this means. And then the star formation rate has been dropping off and is now about 10 times smaller than it was way back in the day. Okay, and way back in the day, years ago, cosmic noon. And SCSS has really always focused on something like this. And MSC is going to do the same kinds of things SCSS did, but way out at much higher redshift, basically a cosmic noon. Or, as my colleague says, basically looking at galaxy evolution when the universe was actually incresting. That's what this is. The origins of MSC. I want to just go into this a little bit because this has been eye-opening for me because I've been involved from the start in this, and just seeing how projects evolve. It's sort of kind of interesting actually. The very but essentially in 2010, 10 years ago now, Canada was doing its long-range plan in 2010. There was sort of I don't think a draft had actually been written, but a group of us had seen what the ideas that had been put forward were. And with respect to the ideas for CFHT and, in fact, just with respect to all the ideas, they were all very interesting. They were kind of what you would expect. And so far, they were a natural progression of what we've been doing. Finishing up ALMA, absolutely essential, it's now made. Continuing with TMT, absolutely essential. Making sure we have our own SKA, absolutely. But some of us were thinking, well, is that everything we want? And I was in a person's office. In fact, I'll come back to this in a second, but I was in a person's office. And I thought, well, really, is this what we want to do? And the sequence of events meant that we proposed MSC, and I'll show you who the people were just in 1 second, actually, here. Why is this making noise? Oh, yeah. So, we came up with an idea, which eventually became MSC. We didn't start off with that name. And for the next couple of years, we spent some time trying to convince people that this was a good idea. And we eventually convinced CFHT that it was a good idea. And that's where things started. And the group of people that I want to highlight here, I don't know how things like TMT started up or ALMA started up. I do know how MSC started up. I was in Patrick Kay's office. And Patrick Kay is a research office up there. I'm sure you've spoken here before, getting to speak, especially about Castor, very cool. And we were thinking, what we'd really like to do is get spectra. And there had been this idea that subsequently died, which was the Gemini WF MOS wide field multi-object spectrograph. And that had just died as a project. It was a big deal at the time because a lot of people worked very hard on it. And my supervisor back in Cambridge had been one of the people who had been involved in that. And we even said at the time that this idea was so good it should be its own telescope. And so we, myself and Pat started talking about, something like that. We should do a sort of a telescope that's just going to do a WF-MOS type of science. And we're like, yeah, that's great. But then with like, well, where could we put it? You know, where could it be? But I was like, oh, well, the CFHT. And I was like, yeah, but no, that's like, we want like a big telescope. And he's like, no, you can put a big telescope. And I'm like, really? He goes, yeah, they've been this study. And I come back to that actually. So they've been this study that shows you can put a much bigger telescope than the CFHT go. He goes, oh, really? That's cool. Like moved on 2 days later, or whatever, there was a postdoc, I think, had a leaving due, or a student was leaving, or something like that. And David Crampton, whom I didn't know at the time, really, came up to me and said, so Pat told me about what you guys were talking about. I was like, okay. He goes, yeah, what do we do now? Oh, okay. And therein, we decided to actually do something. And so then we spent, Pat at the time led what we were calling the NGCFHT, the next generation CFHT, though there's been a few versions of that. And led a great feasibility study. HAA were able to put a small number of resources to show that this idea was technically not stupid, which is the first stage. That's called a feasibility study. But what it means is, are you stupid? The conclusion was we are not stupid in that sense. We then organized quite a large workshop actually in Hawaii, which was very well attended, and eventually managed to pressure the CFHT board and saying, well, actually, you know, this is quite a good idea. Let's do this. Let's try to take it forward. At which point, Rick Marinsky, also big, Sierra Victoria, heavily involved and tons of stuff, another big person to visit. And Derek Salmon, who for many years was kind of CFHT, the director of engineering at CFHT until about a year ago when he retired. We three sort of formed the original version of the project office. Doug Simons was the director sort of that brought us in from the cold, as it were. He sort of basically brought in this NGCFHT group into the CFHT and became MSc, and he's been a strong advocate for us ever since. Jen I was the project scientist in this from 2014 until about last year. Jen Marshall now at Texas A&M University of State from Chi Zito, also from Victoria, State of Advancement, from Victoria, to work at CFHT to be the MSc project manager. And also here is Mary Beth Wajek. And I want to highlight as well this because lots of things happen in a project which you can't control, and most things happen in a project you can't actually control. And so these two have been in particular essential to us. We always knew from the start that we wanted to make sure that this development of CFHT was done in a way that would draw people into the project as much as possible. And Doug Simons has really been a massive advocate for Hawaii astronomy now for many years. So there's a couple of really sort of major programs that we've been embarking upon that MSc supports, which sort of is in the background of, but which are really all being led out to CFHT and are all sort of being led with a vision towards the future. One of these is Envision Mauna Kea. Many of you will be seeing reports in the news about what is happening in Hawaii at the moment with respect to a large amount of protest and a large amount of unrest and a lack of clarity as to what's going to be happening with TMT as the crisis goes in Hawaii. And for those of you trying to sort of get a perspective on how to sort of break through the social media noise, I strongly encourage you to read the Envision Mauna Kea document. It's freely available online at his website. Essentially, when the first round of protests kicked off for TMT in 2015, and we had a lot of people subsequently in the next year or two testifying and doing a lot of public hearings as to the future of the project and essentially what this Mauna Kea means for them. A lot of that was done in a very sort of formal, legal hearing with a lot of public presence. And a group of people from all sides of the project realized, or all sides of Hawaii community, realized this was not a very encouraging forum for discussion. So they decided to set up a different forum, which is essentially, Envision Mauna Kea was designed as a community-based initiative to gather a wide range of perspectives on the mountain's future and to put these valuable insights into the hands of decision makers. And it's a beautiful document because it literally just, they held meetings in town halls and community centres, and people just talked about what Mauna Kea means for them. And that document really has no editing in it. You can sort of hear the people's voices, you know, as they're trying to do everything. And we are not just talking about astronomers here, we're talking about just everybody in Hawaii who wanted to share their thoughts on the future. This is from the preface of the document. So it's a fantastic document that I do encourage you to read. Abu Hit Noah is a crazy name. Many of you will have heard about this. If not directly this, you will have heard of Momo. Very likely you'll have heard of Kuwait. This is the interstellar asteroid, and this is the image of the black hole. And this is, again, a collaboration with MLOA, which CFHC and some of the other Monte observatories are very major on, working hard on. Essentially, positioning-wise, the first place in the world to be traditional indigenous practice in the process of officially naming astronomical discoveries. I thought these were the only, I knew that there were these two plus two other asteroids. And I was actually in Australia talking about MSC start of August, so this was sort of mid to height of the most recent set of protests. Mary Beth actually just let me know this on the night before I was due to give a talk, that just last week, so this would be at the end of July, there were 38 Hawaiian immersion school teachers participated in a week-long workshop to name two new objects. So these are two new asteroids or comets that have been discovered in pan-stars. So this was going on through all of the stuff that you were seeing in the news, so of course not reported as much. There's also Mauna Kea Scholars. Mauna Kea Scholars is a fantastic initiative where literally school apply for time on all of the telescopes in Mauna Kea. And you have 17-year-olds getting time on Keck. And you read the proposals, and they're very good proposals. This is not, they do full proposals, lots of detail, lots of thought, full analyses. They often help out, of course, they have mentors from the observatories and sometimes internationally as well. And it's really just a fantastic way to bring people into the observatories. And again, I think one of the things that's happened over the years, until sort of the big shot in the arm some years ago, there had not been the level of meaningful community engagement that there should have been. That's my own personal opinion, that there should have been. So these sorts of initiatives certainly are very nice to see. So I can't really give a talk on something about Mauna Kea Spectroscope Explorer without, of course, talking about what's going on right now in Mauna Kea. As you know, there's a large number of protesters that are currently trying to block access to TMT so that it can't build in some of the Mauna Kea, for which legally it has now, it's going through various rounds of legal acts and has the legal right to build. Of course, if one does not also have the backing of the community, then that's of course not as important as you think. What is important here, I think, to emphasize is that TMT has in many respects become a lightning rod insofar as you hear a lot of the discussion. It's not just about TMT, it is about TMT, and those who say it's not about TMT, I think that's wrong, but it's not just about TMT. There's a lot of deep-seated issues with respect to astronomy, but also with respect to indigenous cultures in Hawaii. Initially, when I first gave this talk, all of the observatories were augmented due to the fact that they couldn't guarantee access up to Mauna Kea, and particularly access back from Mauna Kea. Mauna Kea is an incredibly high mountain. It's the road, once you get up to the top, it's not good. If there is ever medical emergencies or anything like that, you do not want to have any down to see the fact that you can get people up or down the mountain. So, out of an abundance of caution, as they described it, they did not go to the summit for quite a while, but that's part of the market. However, all observatories are now back and fully functioning, and they're actually taking a detour around the protesters. The protesters said that you can go ahead. Again, the protesters are not protesting astronomy, they're protesting the TMT building. As we alluded just now, this is a very dynamic situation. I have absolutely no idea what is going to happen. I don't think anybody has any idea what is going to happen, but the protest is still going on. The big guy there, Harry Kitten, is helping to lead discussions between the groups is to try to find a way forward. Our hope, and so this was a message that Doug Simons, our director, sent to the MSC collaboration during this time, and I think this is sort of as nice a way of describing things as you can about this week. I look to a future for Hawaii astronomy in which knowledge and worldviews hybridized to create a reality more beautiful and resilient than its progenitors. This is occurring now to the things that I was speaking of. I see a future for Mauna Kea where studies of the universe are buoyed by the wisdom of Hawaiian Kupuna and grounded in indigenous Hawaiian culture. The Big Island community, including MSC, is bigger than that which separates us in the face of adversity. That is certainly our goal, but again, this is something that will be decided by the people who live on Mauna Kea, by the people who live in the Big Island. wanted to mention all that because that is one of the major things as you do any project that you have to deal with. In the public outreach, we always wanted to make sure that we had a very good engagement process, but of course that is particularly important now. And building upon CFHT, which has been there for 40 years, is absolutely an important step in what we're doing. So this is CFHT. This is the cutaway of CFHT. It was built in the 1970s, and Doug says when steel was cheap. Is what it seems right. It's built like a tank, frankly. A fun fact is that Keck is a 10-meter telescope. That's not a fact. You probably knew that already. The fun fact is that Keck is a 10-meter telescope. It's 270 tons. CFHT, a 3.6-meter telescope, is 266 tons. Which means that this pier that the telescope can sit on can support a much, much larger telescope. And you can see there's an awful lot of empty space in the dome, such that you can put on the current pier and essentially an 11.25-meter telescope. You have to replace the dome, that is to say the rotating part of the building, because the slit wouldn't be big enough anyway, because it's designed by people sitting independent. But also, so you have to be replacing it anyway. So that is what MSC would look like, and in fact, from the outside, this would be CFHT, this would be MSC. The two are not identical, but they're very, very similar. And within essentially certainly the same 2D footprint, we do not touch the ground at all. Within the same 2D footprint, we have a 10 or 11 meter telescope. And within the same 3D envelope, we have an 11 meter telescope, which is kind of amazing. This is known that we can do this, and so the fun fact on back, how CFHT influenced TMT, Puello to alter to nefarious. Number two, when the concept of ELTs was just starting up, they weren't called ELTs, in Canada they called them VLOTs, very large optical telescopes. And there was a VLOT study, done saying, well, where could Canada put a really big telescope? And well, which telescopes should we own? Well, CFHT. And so they did a study in the 90s, Sperman et al. And it showed that you could put up to a 15-meter telescope in the current CFHT dome. That then led to the development of Canada's plan for a VLOT, a very large optical telescope, which eventually led them to joining forces with the CELT, which is the Californian Extremely Large Telescope, which was the birth of TMT. Anyway, because that study had existed, Pat was able to say, well, actually, you put a big telescope in the CFHT dome. And yeah, everything seems to work out. MSC itself looks like this. What you have, the building, the bit of that is to say the building bit that does not rotate, is essentially the same. We take off a floor, however, to give us a little bit more space. And down here we keep some of the spectrographs that you're interested in. These are the high-resolution spectrographs, so the ones which look at very, very fine details of the spectrum. You have your 11-meter telescope here. It's a segmented mirror telescope, again using the exact same technologies being developed for TMT and ELT, so leveraging all of that. And up here at time focus, the time focus telescope, you have a sort of set of robots essentially, which position your 4,000 fibers. Your fibers then run down the side of the telescope to either the low resolution spectrographs, which are on the side of the telescopes. These look like Naismith platforms for those familiar with telescope design. They are not Naismith platforms. We do not have a Naismith focus. They're just platforms where we can do so. In this case, these low resolution spectrographs. And right down here, you have the high resolution spectrograph. The dome itself, and you will also maybe have seen better in the previous slide, looks like a sort of mini TMT in terms of the structure. It's a cloth dome. Again, you have it built by Empire Dynamics. And that really is a perfect solution for mass and weight and various considerations like that. And again, the thing with MSC is there's actually no new technology, really. And it's just putting things together in a system that's not put together. And that's where the strength comes from. The MSC collaboration, we're now an international collaboration. You have to do Australian, AAO, it's changed names recently, but the AAO in Australia, Canada, NAOC, France, Canada, France, and Hawaii are still all involved, of course. India is joined, the Indian Institute of Astrophysics. NOAO, which is the US, Texas A&M, which is one institution within the US, and I haven't put it there, but also the UK as of July, have all joined as observers on the project, which is to say they expect to be joining as full members soon, but they want to sort of get a, dip their feet in there. In terms of all the stuff that's going on, in Canada, we've been doing fiber systems, how you get the light, from the prime focus down to the spectrograph. We've been doing dome designs. And this is France. I've been doing the low resolution spectrographs as well as top end, sort of the part of the prime focus units where everything up there sits. China has been building the high resolution spectrograph. This was a meeting in China that we had recently, or a few years ago, sorry. India is leveraging its involvement in TMT, and then we'll hopefully be doing a lot of M1, so primary mirror segments, sort of figuring out how to make the mirror. Australia is providing all the fiber positions to things that actually move the fibers to where you want them in the focal plane, so you can then take the spectrum of the objects you want. And this is MSE as it stands at the end of the conceptual design phase. So you can see everything I showed before. But also that we now have a very evolved design, which has been contributed to by a large number of people. It's yours for only $424 million. I'll be doing a collection at the end of this. We're only $423 million. So, approximately $10 million has been spent on MSC to date. In fact, now slightly more than $10 million to get to that level. Where all of the funds have basically been contributed through efforts and contributions from all of the partnerships that we were able to put together. The next phase, that was the conceptual design. Next phase is about $25 million, and that's preliminary design. And that work is slowly getting off as various communities are getting together their funding. In terms of the timeline, this is the timeline which essentially the duration is well defined. The starting point, or sort of the external milestone, of course, becomes a little bit more hazy with the current situation in my life. However, the plan is for doing preliminary design. It's approximately a 2-year study starting that this year, ending by about 2021. And the master release is the thing that allows you to do telescopes on 1K in the first place. That has to be renewed because it's coming up towards the end. In 2033, if nothing were to change, all the telescopes would have to be up on 1K. That's just the way it is, right? It's a lease space. And so the process to renew that we started about a year and a half ago. It was expected that that process should then finish its first stage next year, and then there'll be a few more years of discussion, after which the new master lease would be approved. Of course, what with the current situation in Hawaii, that timeline, I think, is going to have to be revisited because it's not clear what will happen there. Had that been, if that is the case, however, approval of the construction phase, and we call everything after preliminary design and construction. Essentially, you have a detailed design phase where, I didn't mark it here, but CFHT decommissioning will take place about 2024, and the actual construction of the summit will begin about 2024 as well. That's about a 4 to 5 year process, leading to science commissioning around the end of 2029. And I would just note that here we are the only group who are designing this at the facility. However, every group that does any sort of thinking about the future comes up with the major thing that we're missing. This is from ESO, the Large Aperture Optical Spectroscopy Telescope for the right field of view. ESO would be the major European partners. They believe that this is a massive thing that they need to be doing. The US, in all of their reports, have said that this is a massive thing that they need to be doing as well. And for MSC, that sort of increase in interest, since we've been working on this since 2010, and it's certainly very helpful. And the size team that we have is now 400 scientists in, well, like 397 or something, 400 scientists in 31 countries. As of at least a month or two ago. And so what started off as sort of, a random conversation has certainly grown into something considerably bigger, and we want to be taking to the facility under construction. And right now is a very important time for MSC insofar as all of our partners. Canada is doing its new long-range plan. France is doing its 5-year plan. Australia is doing the midterm review of its 10-year plan. The US is doing its 10-year plan. All of these strategic plans will have reported by the end of next year. And for the sort of sum of money which we're talking about, MXC is essentially a moderate-sized project in the era of extremely large projects. Right? Things like LSST, ELTs, these are billion-dollar things. In fact, multiple billions of dollars of things. MSc is not. Okay, it's actually sort of more along the lines of inflated dollars, building like a Keck-style telescope. But it's at a time when everybody's trying to do big things. So having good rankings in all of those various efforts will be essential. I think as well, likely we need at least one more major partner as well to in order to ensure to have the confidence that we have the resources in order to build this. The board of CFA2 as well, as we saw, for instance, mentioned, worked towards expanding the C partnership to design this facility. So I think the future is looking very good, and certainly, just as well as scientifically, sort of programmatically, just seeing how things happen in a project. And this is where we are now. Where we want to take this is to essentially make sure that MXC can be sort of at the center of that network. Canada is at the center of MXC as well, and is at the center of many of the facilities that you see up there. So it's certainly, I think, a very exciting time, scientifically, of course, technically as well, and even programmatically. Programmatics can be very interesting when you're talking about billion-dollar facilities to look at the universe. I'll stop there now to take questions. Thank you.
Well, that was very interesting. I think astronomy is kind of yoga for the mind. After you see all of the tremendous things that are going on here, it really has to scratch it. My mind is like damaged. There's so much to take in. So I'm sure there's a lot of questions here. Harry?
The fiber positioning system, is that old technology or to be developed technology?
It is based upon technology that already exists. So there was an instrument called FMOS and Subaru, which used essentially tilting spines. They're literally spines that are actuated by a little magnet, essentially, that shifts the spine and tilts it to different positions. That instrument never did that great science, to be honest with you, but the Australians developed the technology for that. And Foremost, which is essentially a 4-meter class version of MSE, which will see first light in about 2 years' time, it's using that technology as well. We are copying them because it has a lot of very nice characteristics. For those of you interested in such things, the original positioners were called Echidna, and our positions are called Sphinx. Sphinx being the daughter and or granddaughter of Echidna. So the Greeks are kind of.
So how long is it going to take to position and reposition 4,000 sensors?
30 seconds.
30 seconds?
No, 2 minutes.
2 minutes.
But everything should be done within 30 seconds. So yeah, so it's basically you can do all of them simultaneously. And essentially it's about, on average, there's a big move and then there's a precision move. And then there's a small number of them that require an additional move after that.
4,000.
Yeah. So no, it's incredible. So there's 2 types of positions that use. So this is one type. There's another group that there's another type of technology that also tries to do this. But the position times have to be very short. Again, you're trying to. All of these facilities are at their heart, survey facilities, survey machine. So one wants to have the maximum efficiency as possible. So it's a lot of precision metrology that's required.
Any questions? Lori?
What's going to happen to all the data?
Yes, so so the data for MSC has become sort of like a bear pit of people wanting to actually be the one that's responsible for it. So yeah, so the data is going to be essentially, it will be processed from the sort of taking just the raw pixels off the telescope. It will be processed through, instead of removing all of the instrumental signatures, firstly of course, and then also all of the spectra extracted in a very homogeneous way. So regardless of what you were wanting to do with that object, there will be a level of data processing which basically gives you the final spectrum and says you can do whatever you like with it. Now, that will then be all queryable through a database. You don't need to use those spectra that have been provided, I should say, but there will be this level of getting the data to sort of the science-ready position. And people who want to do something more sophisticated can go back and grab the data themselves and do a more sophisticated analysis. But what facilities, particularly I think SCSS, really showed the way is that by having a database that's easy to query, and having data that's already well understood and well calibrated and dealt with already by the people who know about the data, maximizes the science by factors of 100 over what might otherwise be. A major barrier in doing science for so many people, to do science as an astronomer, is understanding the data, understanding how to process it. When you have something like this volume, you need to be able to do all of this sort of centrally. You need to be able to provide the sort of the science-ready data products to the community, because they have to be able to sort of make sense of this enormous data set. Our data challenges, while they sound sort of extreme, are nothing compared to something like LSST. LSST, the rate of data that it takes and the volume of data it takes is just obscene. So MSC is big data, but it is going to exist in the future when it's going to look like really small data compared to LSST, and particularly compared to SKA, where SKA produces an internet every night or something ridiculous.
I have a couple of questions. One thing is that when you rapidly showed the diagram, there was a hole in the center, which I assume is not a Cassegrain type system. It's just basically it's in the shadow.
Yes, so basically you have the primary mirror has a hole in the center. So yeah, so basically we have a big circle obscuration, so you're not going to get anything there anyway. But that's also where we put a metrology camera, which then is a camera pointing up. It's actually a telescope pointing up to the top end of the telescope, so that we can then measure the positions of where everything is very precisely at the top end. So it has a dual purpose. You're not going to get anything like there anyway because of the central obscuration, but also we need somewhere to put the camera that's looking at our own telescope to tell us where things are.
Interesting. So basically what it is a prime focus instrument with fiber optics relaying
Exactly.
down
Exactly. And we did a big study as well, so whether this should be prime focus or whether we want the CATS focus or things like this. And it turns out that while you could make a CATS telescope be somewhat bigger, it turns out you have to make it substantially bigger in order to actually be more efficient at collecting photons, because the size of your secondary mirror in the Cassegrain model actually blocks out so much light that you're as well just having the prime focus in the first place. There's also various, we actually did a very detailed study of this. It also turns out that where you would have to put all your science instruments in the Cassegrain model, none of the engineers could figure out how you could then get into that space to fix things if they ever went wrong. And so these sort of things we can. So yeah. So prime focus was the solution.
What would the length of an exposure be?
So so typically, I think the average length is going to be an average target will probably be looked at for something like an hour, but the actual exposures might be anything ranging from 10 minutes to about half an hour. We're going to we have a very broad wavelength coverage covering from the sort of 360, so UV, U band, all the way through to J band in the infrared. And it turns out that for the reddest optical detectors at about 1,000 nanometers, cosmic ray hits are so severe that you probably don't want to be exposing for much longer than about 10 minutes per exposure. So there you just take lots and lots of 10 minutes exposure and then add them up. So again, you have lots of different cameras in the spectra working in different wavelength ranges. But I think sort of on average you're probably looking at about 15-minute exposures. And maybe 1 hour total on target. Again, the thing with this as well, we're trying to get really faint, and I maybe didn't emphasize this enough, but with things like SCSS already having existed for many years, and with things like Foremost about to exist, there's no point, all of the bright stuff has been done, or certainly there's no point building a $400 million facility to do something that you could actually do with a 4-meter facility, $80 million. And so therefore, longer exposures is going to be critical in order to really take full advantage of the light collecting power of MSC to really push those things as hard as they can see otherwise.
I think it's just amazing the synchronicity where we have Gaia as kind of an appetizer that developed a tremendous appetite for radial velocity, so you can put both things together and really get much more accurate.
Gaia is really, as a colleague of mine described Gaia as maybe not fundamental in terms of telling us about the nature of dark energy, but foundational in terms of, starting now, everything is referenced to Gaia. All astrometric systems, all positions, all magnitudes, everything will be referenced to Gaia, because what they're producing is utterly exquisite.
Are there any more questions? Well, thanks so much, Ellen, for sharing this exciting future view, and I do wish you all the best at selling this project and getting more people to join in and make it happen.
Thank you very much. Thank you.